Hello, everyone. So this is the third part of our lecture series for functions, limits, and continuity. And if you have watched my previous videos, I showed you the formal definition of functions, how to look for the domain and range of a given function, and I also presented to you the different types of functions as algebraic and transcendental functions. And also, I taught you how to sketch the graph of a given function. So in this video, I'm gonna show you how to find the limits or how to evaluate the limits of a given function. So by the way, functions, limits, and continuity are three essential topics in the study of differential calculus. Okay, so let's start. And here is the formal definition of the limits of a function. Okay, if we let f be a function at every number in some open interval containing a, except possibly at a number a itself, then the limit of f of x as x approaches a is L, and that is written of the form limit of f of x as x approaches a is equal to L, if and only if the following statement is true. Okay, if given any epsilon larger than 0, however very small, there exists a number delta greater than 0, such that if the absolute value of x minus a is greater than 0 but less than delta, then the absolute value of f of x minus L is less than epsilon. This is what you call the delta epsilon neighborhood. And this definition states that the function values f of x approach a limit L as x approaches the number a. Okay? If the absolute value of the difference between f of x and L is very, very, very small, and that is obtained by taking x sufficiently near a but not equal to a. So we are just going to get those numbers on the right side of a and those numbers on the left side of a. Okay, and this definition can be taken geometrically as this. Okay, so if we let this the function f of x, and then we choose a number a here. Okay, and since from the definition we say that x cannot be equal to a, okay, except possibly at a itself, and then which means f of x or f of a cannot be equal to L. F of a is not equal to L. Okay, then if we choose a number a minus delta sub 1 or plus delta sub 1, that's a number on the right side. So if we choose a number on the right side of a and we let it to be a plus delta sub 1, and then we will notice that, okay, the function value approaches L, and that is L plus epsilon sub 1. And then if we choose a number on the left side of a, say a minus delta sub 1, and then what we observe is that the function value still approaches L, and that is your L minus epsilon sub 1. And even if I choose a number very, very close to A, okay, you will observe that the function value will still approach L. Okay, that is what we mean by the limit of f of x as x approaches A is equal to L. Okay, and here are the limit theorems that we might want to consider. Okay, so if we let f and g be functions and we let a be element of the real number, then if c is constant, then the limit of constant as x approaches A is equal to the constant itself. And if c is constant, then the limit of cx as x approaches A, and then is equal to this c, you can throw it outside. So c limit of x as x approaches A, which is equal to CA. What you observe is that one easy way to evaluate the limit of a given function is by straightforward substitution, or it's a direct substitution. Okay. And for the limit of a linear function, the limit of mx plus b as x approaches A is equal to ma plus b. Theorem 1.1.4, this is the limit of sums is equal to the sum of their limits. And then theorem 1.1.5, that is the limit of f of x times g of x as x approaches A. If the limit of f of x as x approaches A is L, and the limit of g of x as x approaches a is m, then the limit of the product of f of x and g of x as x approaches a is equal to L times m. And theorem 1.1.5 can be expanded of this form. Okay, the limit of x f sub 1 of x times f sub 2 of x times until f sub n of x as x approaches a is equal to L1 times L2 running until Ln. And other theorems are as follows. Okay, for any n positive integer, then the limit of f of x to the n as x approaches a is equal to L raised to n. And this is the limit of f of x over g of x as x approaches a is equal to L over m. And for any n positive integer, then the limit of the nth root of f of x as x approaches a is equal to the nth root of L. And for any a real number except 0, then the limit of 1 over x as x approaches a is equal to 1 over a. And 1.1.11 states that the limit of the nth root of x as x approaches a is equal to a. The nth root of a, yeah. Yeah, right. And 1.1.12, the limit of c all over x raised to n as x approaches infinity is equal to 0, where n element of positive integer and c any constant. So this is what you call the limits or limits at infinity. Okay, so infinity here is represented or infinity here represents a very, very large number. Okay, and this theorem can easily be understood by using the function f of x is equal to, say, 1 over x. And then geometrically speaking, so the function 1 over x can be thought this way. Okay, so I'll do it on the other side. And then, as you can notice, as x approaches a very large number, okay, say positive number, positive infinity, a very, very large number. And then what you notice is that as I get closer and closer to positive infinity, the function value f of x gets closer and closer to 0. And this is the definition of the asymptote, that if the limit of f of x as x approaches infinity is equal to 0, then the line y equals 0 is a horizontal asymptote. And as you can notice, as x approaches negative infinity, okay, on the side, okay, going to the left, a very large number but negative, the function value f of x still approaches 0. Okay, and that means that the limit of c all over x raised to n as x approaches infinity is equal to 0. Okay, let's have some illustrations. Number 1, we find the limit of 4 as x approaches 2. And then by theorem 1.1.1, we say that the limit of a constant is equal to the constant itself. Say the limit, we recall that the limit of a constant as x approaches any number is equal to the constant itself. So we might thought that the limit of 4 as x approaches 2 is equal to 4. And this can be thought geometrically as this. Okay, say this is your line y equals 4. And then we choose a number, 2. Okay, since the limit of 4 as x approaches 2. And then what you notice is that as I choose a number getting closer to 2, my y or my f of x is still equal to 4. Okay, if I choose a number here, okay, what you notice is that my y is still equal to 4. And if I do it on the other side, as I get closer and closer to 2, my function value is still equal to 4. Okay, another one. Say we evaluate the limit of negative 1/2 as x approaches 2. Okay, and this is your y equals negative 1/2. And if you do the same, as you get closer and closer to 2, the function value get is still equal to negative 1/2. That's why the limit of negative 1/2 as x approaches 2 is equal to negative 1/2. Okay? One more. Say the limit of x squared minus 2x plus 3 as x approaches negative 2. And then again, by applying the theorems, so this is the limit of sums is equal to the sum of their limits. So we say that the limit of x squared minus 2x plus 3 as x approaches negative 2 is equal to the limit of x squared as x approaches negative 2 minus 2, the limit of x as x approaches negative 2, plus the limit of 3 as x approaches negative 2. And then by direct substitution, we say that the limit of x squared as x approaches negative 2 is equal to the quantity negative 2 squared, and then minus 2. Then the limit of x as x approaches negative 2, you just replace x by negative 2. So that's negative minus 2 times negative 2. And then again, the limit of constant as x approaches negative 2 is equal to the constant itself. So that's the limit of 3 as x approaches negative 2 is equal to 3. And simplifying further, so this is equal to 4. Negative 2 squared, this is equal to 4. And then negative 2 times negative 2 is still, this is equal to 4. 4 plus 4 plus 3, and that gives you 11. Okay? One more. Say the limit of the quantity of 2x plus 3 to the third power as x approaches negative 1/2. Again, by direct substitution, that can be thought as 2 times negative 1/2 plus 3 raised to the third power. We know that 2 times negative 1/2, this is equal to negative 1 plus 3, that's equal to 2 to the third power, and that is equal to 8. Okay? So the idea is we are just directly substituting this value a to x on the given function. Again, we are not saying that the value of this function is equal to, say for this one, we do not say that the value of x squared minus 2x plus 3 when x equals negative 2 is equal to 11. We are, since x cannot be equal to negative 2, then f of x or f of negative 2 cannot be equal to 11. That's the idea of the limit of a given function. That means as you get closer and closer to negative 2, the value of your f of x gets closer and closer to 11. Okay? One more. Say the limit of x squared minus 16 all over x minus 4 as x approaches 4. Okay? We know that when x is replaced by 4, this is what happens. So you have 4 square minus 16 all over 4 minus 4. And you know that 4 square is equal to 16. And then that gives you 0 over 0. And we know that division of 0 is not allowed. And 0 divided by 0 is what we call an indeterminate form. Okay? One more. So what are we going to do now is we simplify x squared minus 16 all over x minus 4. And the limit of x squared minus 16 all over x minus 4 as x approaches 4 can be thought as the limit of x plus 4 times x minus 4 all over x minus 4. And you just get the factor of x squared, the factors of x squared minus 16. This is equal to x plus 4 times x minus 4. And you can now cancel this out. Okay? And therefore, we can simply write it out as limit of x plus 4 as x approaches 4. Okay? So once again, considering x squared minus 16 over x minus 4, we know that the domain of this function is the set of real number except negative 4. Or except 4, sorry, that's except 4. Okay? Because when x is equal to 4, the denominator will become 0. However, when x equals 4, so we just replace x by 4 here. So we have 4 plus 4, and that is equal to 8. Okay? So which means when x is equal to 4, the function value is equal to 8. And since x is not equal to 4, then we can say that f of x cannot be equal to 8. And that can be taught geometrically as this. Okay? So we will be tracing the function f of x equals x plus 4. And this is your f of x equals x plus 4. Okay? And then we know that x cannot be 4. Okay? X cannot be equal to 4. That's why y cannot be 8. So this is what we call the point discontinuity. That's why there's an open hole here, which indicates that x cannot be 4 and f of x cannot be equal to 8. Again, that is what you call the point discontinuity. Okay, and as we observe, as we get closer and closer to 4, the function value gets closer and closer to 8. Even if I do it on the left side of 4, say I pick 3.999999. That's a number closest or closer to 4. Okay? So the function value here, is still equal to 8. And that could probably be 7.999 something. Okay? That's how we do it. One more. Say we want to evaluate the limit of 1 minus the square root of x all over 1 minus x as x approaches 1. Again, when you replace x by 1 by direct substitution, so you obtain 0 over 0 because this will become square root of 1. So we have 1 minus square root of 1, that is 0, all over 1 minus 1 is equal to 0. So once again, we must do something with the given function. Okay? Whenever after substituting the value a to the given function, and we arrive at 0 over 0, and then other indeterminate form, we might also include infinity over infinity. Okay, infinity minus infinity, 0 raised to 0. Infinity raised to infinity. These are the other types of indeterminate forms. Okay, so when we arrive at this expression, so that gives us the hint that we must do something. We must manipulate, or we must simplify the given function algebraically. And that is what we're going to do on this part of our given. Okay. So what I'm going to do is I need to eliminate this 1 minus x. We need to avoid this 1 minus x because this 1 minus x gives 0 when x equals 1. So what I'm going to do is I will rationalize the numerator. Okay? And that is obtained by multiplying both the numerator and denominator by the conjugate of the numerator. The numerator is 1 minus square root of x, and the conjugate of 1 minus square root of x is 1 plus square root of x. So I need to multiply both the numerator and denominator by 1 plus square root of x all over 1 plus square root of x. Okay, and 1 plus square root of x over 1 plus square root of x can be simply thought as 1. And then simplifying, we have this. Okay, so when you multiply these two, so this exhibit sum and difference of two binomial with similar terms. Once more, it's sum and difference of two binomial with similar terms of this form. Say x plus y times x minus y is equal to x squared minus y squared. So we just simply multiply 1 times 1, that is equal to 1. Square root of x times square root of x is equal to x. And then we just affix it with minus sign. So that's 1 minus x. All over, on the denominator, you just multiply this 2. Okay, so we can now cancel this out. We can now remove 1 minus x. And that leads us to the limit of 1 all over x plus the square root of x as x approaches 1. And then we can now replace x by 1. And that is equal to 1 all over 1 plus the square root of 1. And finally, the limit of 1 minus square root of x all over 1 minus x as x approaches 1 is equal to 1 half. Okay, another one. This time I'll do it in cube root of x minus 1 as all over x minus 1 as x approaches 1. Okay, by direct substitution again, let me see what happens. Okay, we have cube root of 1 minus 1 all over 1 minus 1, and this gives you 0 over 0. Okay, next. So what are we going to do? So we need to simplify the given function algebraically. Yeah. Okay. So what if, just like what we did on the previous example, what if we multiply this by the conjugate? So we have cube root of x plus 1 all over cube root of x plus 1. Because the conjugate of cube root of x minus 1 is cube root of x plus 1. And then we can now have limit, say, as x approaches 1. And then I write the vinculum here. And then you multiply the numerators. So you have cube root of x times cube root of x is cube root of x squared minus 1 times 1 is 1 all over x minus 1 times the quantity cube root of x plus 1. Unfortunately, this numerator cube root of x squared minus 1 cannot be taught as x minus 1. So you cannot cancel this out. Okay? So which means multiplying this by the conjugate of the numerator will not help us solve the issue. Okay? So what are we going to do? Okay? So we think of an expression equal to x minus 1. So by the way, x minus 1 can be written of this form. Cube root of x to the third power, that is still equal to x, minus 1 to the third power. So this cube root of x cubed minus 1 cubed is still equal to x minus 1. So what did you notice now? This exhibit difference of two cubes. Say, we recall, sorry for my handwriting, we recall that the factors of x cubed minus y cubed is equal to x minus y times the quantity x squared plus xy plus y squared. Okay, so we might use this pattern to resolve the issue for x minus 1. So we have x minus 1 is equal to, where x is represented by cube root of x and y is represented by 1. Okay, so you have x, so that is represented by cube root of x minus 1 times x squared. So you just square this. So that's cube root of x to the second power plus you multiply these two, cube root of x, and then you square the second term. Sorry. So that's 1. So this is 1. Close. And then when we go back here, so this cube root of x minus 1 is already given in here. Okay. So what are we going to do is we will multiply this numerator and denominator by this expression. Cube root of x squared plus cube root of x plus 1, so that when multiplied to this, we will arrive at x minus 1. And that's one way to rationalize cube root of x minus 1. Okay, let us multiply it. Okay. So again, when you multiply this cube root of x minus 1 times cube root of x squared plus square root of x, sorry, this one is cube root, by the way. This is cube root. Okay, that's cube root of x plus 1 all over cube root of x squared plus cube root of x plus 1, and that leads us to the product of the numerators is equal to x minus 1 all over x minus 1 cube root of x squared plus cube root of x plus 1 as x approaches 1. Okay, and then finally we can cancel this out. Okay, and then we can now have the limit of 1 all over cube root of x squared plus cube root of x, okay, plus cube root of x plus 1 as x approaches 1. And then we can now replace x by 1 to evaluate its limit. So we now simply have 1 all over cube root of 1 square plus cube root of 1, okay, plus 1 and that is simply equal to 1/3. So therefore, the limit of cube root of x minus 1 as all over x minus 1 as x approaches 1 is equal to 1/3. Okay, let's have some more. Yeah. The limit of 2 all over x cubed as x approaches infinity. And this is limit at infinity. Yeah, limit at infinity. Okay. So this example can be illustrated by applying the properties of this graph. Okay, let me just show you the graph of 2 over x cubed. So we let f of x equals 2 over x cubed. Okay. So obviously when x is equal to 1, y is equal to 2. And then the graph of this function can be drawn this way. I'll just smoothly trace it for you. Okay. And then whenever x is negative, so this is raised to the third power, so which means y is still negative. So when x is negative 1, y is negative 2, I think. Yeah. So we might eventually do it that way. Okay. And then on this side. Yeah, yan. Good. Okay. So we try to enumerate the characteristics of this function. We know that the domain of this function is the set of all real numbers. Okay. The set of real numbers except 0, and that the range of this function is the set of real number, okay, except 0. Okay. And we know that, let me see, as x approaches infinity, f of x approaches 0. So as x approaches negative infinity, your f of x also approaches 0. So which means the limit of 2 all over x cubed as x approaches a very, very large number, this infinity. And that is equal to 0. So 2 divided by a very, very large number is equal to 0. One more. Say the limit of 3x cubed minus 2x plus 4 all over 2 minus 3x squared minus 2x cubed as x approaches infinity. Okay. So one way to do this, when you replace x by a very, very large number, that will not help us solve the problem. So what I'm going to do is we will be taking into consideration the highest powers on both the numerator and denominator. So in this case, we have to the third power. Okay. So we will be dividing each term on the numerator and denominator by x cubed, since x cubed is the term containing the highest power. Yeah. Okay. So this is what will happen. Limit of 3x cubed over x cubed minus 2x over x cubed plus 4 over x cubed all over 2 over x cubed minus 3x squared over x cubed minus 2x cubed all over x cubed as x approaches a very, very large number. That's infinity. Okay, and then simplifying this algebraically, we have 3x cubed over x cubed, and that is equal to 3. Okay, then this is minus 2 over x squared. Yeah, that's right. Plus copy 4 over x cubed. On the denominator, we have 2 over x cubed. Yeah, minus 3x squared over x cubed. So we can remove this x squared, and then this will become 2. This will become 1. Okay, so you have 3 over x, yeah, and then minus 2x cubed over x cubed. So you cancel this out, and you have 2 here. And then you can now replace x by a very, very large number. Okay, that's it. So by principle, again, we recall that the limit of a constant number all over x raised to n as x approaches a very large number and n element of positive integer is equal to 0. So this will become 0. This will approach 0. This will also approach 0. This will also approach 0. And what is left on the numerator is 3. and on the denominator is negative 2. And therefore, the limit of 3x cubed minus 2x plus 4 all over 2 minus 3x squared minus 2x cubed as x approaches a very large number, that's infinity, is equal to negative 3/2. Again, you recall the property of the horizontal asymptote. Okay? So when you were given a rational function p of x all over q of x, and if the degree of the numerator, n, is equal to the degree of the denominator, say m, in this case that's 3, then the line y equals negative 3/2 is a horizontal asymptote. And that confirms that whenever your x approaches a very, very large number, your f of x will approach negative 3/2. And this is the definition of the horizontal asymptotes. And I guess that's the last one. Yeah. So that's it for now. And I'll see you next on my next video. Goodbye, everyone.